Swayam Prabha. Digital India. Educated India.
So yeah, I think so. Today's session is around the future of compute. I think we have had a pretty hectic 2 weeks of talks from professors and then from some of the HP enterprise folks. I think talking about things which they have been um, looking at, areas which they've been looking at. So it's been kind of a theory to practice kind of session. And now this final session is. It's more of a perspective. So the future is always a perspective. So I don't think you can always. Um, did the presentation go away?
No, sir, it's visible.
It's there. Okay. Okay. For me, for some reason, it just went. Okay. Yeah. So yeah, like I said, it's a perspective. So it's not something which anyone can predict very well. I think it's always things always change. They always turn out differently from what people have been thinking. So um, if I want there to be a lot of discussion around this. I think it can present what we think is the trends, what are the problems, and where things seem to be heading, and then we can have a discussion around what people feel, and like also we can talk about some of the things which are happening uh, in Hewlett Packard Enterprise in terms of futures in the labs, and Superna in fact works in the HP labs team. So I think can also talk about some of the things which are happening as future research. Like the labs does more of like research which is like 3 to 5 years or even beyond kind of thing, and then there are we have some of these advanced development groups within the business units which look at the near future, which is from like two to 3 to 4 years kind of thing. So it's so you get that kind of uh, segmentation, I think, going from the labs to the BU, and then the labs come out with things which um, might make sense for the business to look at, and then the business unit looks at some of them. So I think we can talk about both from the business unit perspective as well as the labs perspective, things which are happening. And yeah, so looking forward to a discussion kind of thing. So I think I will go a bit slowly. And the other thing I wanted to tell before I start is that this presentation might seem focused on hardware, so it might seem um, kind of orthogonal to the course structure, but I think there is a lot of relevance. I mean, you need to understand what's happening in the hardware side to be able to figure out what you need to do on the software side. There needs to be a lot of co-design of both of the things. So I think you need to understand that, and then we will talk about software aspects, especially I think uh, with Superna. I think at the end, I think so. Hope it will be useful. So stop me whenever you want. I think as always, and want this to be more of a discussion. So to start again, as always, I have to start with the Calvin and Hobbes. So I think this one is apt for this because I I hope it will make sense for some of you, but it can be confusing too. So let's start with what is the motivation. I mean, what's happening, what has happened over the last few decades of computer science, and then where we are going, and what are the challenges today, and what are the problems being solved because of that. So the first thing which we see today as a trend is the data explosion, right? I think all of you would be aware of this and would be seeing it in your daily life also. Uh, when I started in in the industry, in the computer science industry, I think the IT industry, I think the main things were databases. I think the enterprise applications, if you saw, basically they were databases. And if you see on the left hand side, Walmart's transaction database apparently right now is around 40 petabytes. So that seems quite huge now. It used to be much smaller when we started. I think the Oracle databases and the IBM databases and things like that. But then it's grown to around 40 petabytes, and this is structured data, so it's basically based on people inputting things. So it's mostly, if you can think of it, it's the paper trail to the digital trail kind of thing. I mean, recording of what was there on paper on the digital this thing, to be able to do transactions fast enough, things like banking and um, things like that. So that it was all kind of very structured data in nice tables format, and you could easily kind of do the analytics on it where required. But then this has changed, I think, over the last decade or so, I think maybe more, especially with Facebook and some of the social applications coming in. The amount of data has increased to like 4 petabytes a day. This is on Facebook today. I mean, I think this is a slightly old data, so things would have changed even more by now. But it was 4 petabytes a day in 2017 in terms of the data on Facebook across 2 billion users. So it still seems small. It's around 2 MB per active user, but it's probably grown even more today. And this data is not as structured as what we saw with the databases and things like that. So there is a lot more challenges in being able to analyze some of this, and I think that's where some of the machine learning part is also coming in. We'll talk about that also later. And then finally, I think what we are moving towards is not just unstructured data. It's a lot of uh, structured and unstructured data coming from sensors, from the edge and things like that. And especially with connected cars, I think you can see that it's expected to go into the exabyte range of data. So that's a lot of data to be maybe transferred over to a cloud or something, and do some processing on it, and that is no longer feasible for all of the data. So I think what's happening more is that there has to be something which happens at what is known as the edge, and there has to be some processing which happens at the cloud, and then there has to be some kind of communication between them to be able to process the data better. So this is where things are moving, and this kind of also defines how the software is moving and the hardware is moving to be able to handle this kind of data. The other thing with the right hand side data is not just the fact that it is so huge. The other challenge we have is that the responses have to be real time. So you have to kind of handle this data and be able to do analytics and be able to respond in real time. You don't want it to go to the cloud or something and come back, and by that time you would have an accident probably on the road. So you can't really do that. So it has to be pretty much real time kind of processing and responses which have to happen. So it puts a greater load on the infrastructure which has to handle some of these things. So this is the problem as we see it today. Or you can see it as a motivation. Of what's happening and why things need to change. So what's happening on the compute side? So on the compute side, things are not keeping up. I don't know how many of you have studied Moore's law in your engineering degree. Um, but basically, Gordon Moore was a person who came out with this theory that the transistors will grow smaller and smaller, and it's every 18 months to uh, 2 years. I think you will see doubling of the frequency, maybe a doubling of the number of transistors on a chip and things like that. So this was kind of his prediction, and it kind of stayed true. In fact, I think people went to the extent of making sure that they followed Moore's law. I think ITRS is an agency which comes out with how the feature sizes are defined. So if you know what a feature size is from your electronics courses and things like that, it's the gap between the source and the drain of a transistor, right? So I think that kind of definition of that in terms of what it should change, if it changes like in a ratio of 0.7 from one generation to the next, then because it's a length kind of thing, an area would mean it's a square of it, and so you would get a doubling of uh, the performance, or a reduction by 2 of the number of transistors which are there, or the transistor sizes which are there. So that is the kind of prediction which ITRS came up with based on Moore's law. So it's all kind of depended on Moore's law, and so everything was nice. I think from 1975, I think when it all started, I think with 180 nanometer processes in processors, I think it kind of kept on improving generation by generation, where the feature sizes would go down by a zero point 0.7. So that's another thing I think, which I'm not sure if you realized. I think if you've ever thought about why the feature sizes come down by zero point 0.7, right, from generation to generation. That's because of this trying to keep up with this Moore's law kind of thing. So that's the idea. So if you see now, I think we have 10 nanometer technology which is coming out now. I think the previous generation was 14 nanometer. So if you see the ratio, it's 0.7, and then the next one is supposed to be 7 nanometer, and then we are supposed to go down to 5 nanometer and 3 nanometer, and so on. I mean, hoping we can really scale to those small levels. But because those feature sizes are going in that ratio, I think you're able to double basically you're able to reduce the transistors by half. Their sizes go down by half, so you can have that many, double the number of transistors on a particular chip. And the best part of this was there was another law which was called Dennard scaling, which basically talked about the power consumption when this happened. And the power density kind of uh, would remain constant according to Dennard's scaling. So in the sense that even if you go down by a factor of zero point 0.7 on the feature sizes for the transistors, the power consumption would also go down by that same factor. So you could actually have more transistors on a chip, and with the same power envelope. So that turned out to be really cool, right? I think you can actually put more transistors on a chip, and then you get more performance, but at the same power. So this was really cool. I think so you saw this nice gradual increase from generation to generation. But then this at around 2010 time frame, the Moore's law started dropping off. Actually, it's probably uh, a bit later, but Dennard scaling stopped even before that. So I think the fact that you could maintain the power density was no longer true. And I think the right hand side, what I show is actually a graph from the Hennessy and Patterson ACM Turing lecture, I think, which I think was also posted by Adi, I think, in the discussion we had on last Saturday. Uh, so I missed that session, but I saw that he had posted that link. So that talk, I think, he presents this slide where he shows that the power and the technology have kind of, they hit an intersection at some point, and then the power has started increasing since then. And this is also because as you go to these smaller feature sizes, the smaller nanometer process sizes, I think the leakage current increases, and we are no longer able to sustain the power envelopes which are there. So that's becoming another challenge, to be able to increase the frequency of a single um, CPU. And what if you see on the left hand side again, you see the transistors, I think, kind of plateauing at around 2015 time frame. But what we also saw was that the single thread performance started to plateau even before that. I think you couldn't really increase the frequency also of a particular processor beyond a range, even because of these power issues and things like that. So what started as a trend was that around 2000 2005 timeframe, I think we started getting into this multi-core era, and that again changed the whole software paradigm, right? I think till then everything was single threaded, and software was designed for that kind of hardware. And then we started getting multi-core so that we could put more of these transistors on a system, and then get more performance out of it in the same area kind of thing. And because you had these multiple cores, the applications also started changing to be able to use these multiple cores and in their application. And so you see the number of cores also started increasing. So since 2005, if you see now, I think you will probably see in the range of um, for instance, on the Intel Xeon side, I think with the latest Ice Lake generation, you see around 40 cores on a single socket. So a single CPU is now having 40 cores, and on the AMD side, it's even higher. Probably it's around the 60s, I think, with the some of the newer AMD and the ARM cores, which are ARM sockets, which are coming out. So it's a lot of cores which are there, and software has to handle that. And again, this leads to another law which we've talked about in probably computer science, called as Amdahl's law, where we know that things cannot you cannot parallelize too much, right? So even if you have like 40 cores, you can't write an application which scales beautifully, like, I mean, from 1 to 40, and it goes like 40x or something like that in terms of performance. That's not true. What typically happens is that there is some part of the code which you cannot really parallelize, and that limits your performance, and that's what Amdahl's law is about. So we are hitting those kind of limits with software too. So we can't really keep growing the number of cores and expect that we will get scaling in terms of the performance. So these are some of the challenges which we are seeing in hardware. And so the hardware industry has had to react to, the processor industry has had to react to some of these things. And at the same time, I think yeah, we'll talk about more about how the workloads have changed, and so which has probably helped us move from this kind of vicious cycle, right, where we are not able to really get much out of Moore's law, and we are not able to really scale processors like we could do in the previous generations. So any questions on this slide? If you've understood this concept well, I think it'll help as we move forward. Okay, so if there are no questions, I think this is another slide, I think, from the same Hennessy and Patterson talk. So I think it kind of talks about what I was mentioning, right? I think their talk is probably more of an evolution from CISC to RISC, and I think why RISC is cool naturally because they are the inventors of RISC, I think. But this also gives you that idea that um, the scaling was pretty nice, I think, in the first 3.5 years. Then with RISC, I think over the last 30 years or something, I think there was pretty good scaling. And then we had the end of Dennard scaling, I think, which coincided with where we had to start doing multi-cores to be able to handle that same power envelope and have scaling at the same time. And then we started hitting Amdahl's law, of course. So we are not able to really scale performance out of the application at this point. And since 2015, I mean, we are not really growing. So I think, have we reached the end of the line? That's some of the questions, I think. If you see the process, the feature sizes also, like I said, we've gone to 10 nanometer now. 7 nanometer is expected pretty soon. I think we will achieve that. But then would we really get to 5 nanometer or 3 nanometer and things like that? I think it's entering the realm of quantum mechanics, right? I think you cannot probably have too many of these electrons out there and be able to get realistic, reliable kind of switching of transistors and things like that. So we are going to probably end up in some kind of challenges in terms of the silicon processing itself to be able to create processors which go beyond like 5 nanometer or 3 nanometer and things like that. So it's a time when we have to retrospect and think whether we continue on the same path, or is there something different we need to do to be able to handle the requirements of the next generation of compute. The other thing which this slide shows is on the right hand side, it shows DRAM. So DRAM, I believe, has even greater challenges than processors in terms of scaling. Even DRAM, I think the nanometer thing has come down. I think has reduced from generation to generation, but it's probably higher than processor. But then I think we are at that stage where again we are not able to scale much, and I think what they had started to do is they have started to stack some of these DRAM chips to be able to get the higher capacities as we go to the newer generation. So that again leads to a lot of reliability issues and things like that. So I think there's a lot of challenges in being able to scale DRAM, which are probably more than what we are seeing on the processor side. So the other thing is that this scaling, which is end of scaling as they call it, is probably happening at the wrong time, right? Like I said, I mean, again, this is a throwback to that first slide which I talked about, where about the data, right? I think we are seeing number of people with connected devices, like which is increasing. The social infrastructure is increasing. The apps is increasing. So this gives an idea of like where things are going. So if you look back to like I said, when I started in the industry, I think we had these systems of record, right? I think basically where we are saying that we are recording whatever we are doing, and that was in those structured databases. Then we moved to this systems of engagement, which is like the social era, where it's based on social interactions and like data which is collected from those interactions. Say someone tried to buy something from a particular shop, and then you track that, and then you throw up an advertisement for that person and things like that, right? So those are kind of social interactions which resulted in the systems of engagement. And now what we are getting is into the systems of action, which is the edge era, right? With things like connected cars, like I talked about already. And here I think it's interesting that they've shown the Olympics as a landmark item in 2020. It's now 2021, of course, but then the expectation is that at that time, I think we were going to have 8 billion people there with 20 billion mobile devices, 100 billion social infrastructure, and 1 trillion apps. So I mean, if you get all this data out there and you have to process it, I think it really becomes a huge challenge, and that's what we are looking at. The other challenge which we've been seeing, I think, and you would have noticed this if you read the tech news, right? I think is the fact that we have been getting these security challenges. I think Spectre and Meltdown, and there are more of these happening every year. And why is this happening? It's, if you try to sit back and think and like why it's happening, it's again because of kind of Moore's law, right? I think every year things were getting faster. So there's more CPU, more frequency. So how do you keep up, right? I mean, how do you do more processing per clock? So and then so the way you have to do it is you have to do it through caching and technologies like that, which and speculation. So processes became more and more complex during that time frame, right? With speculation and out of order processing and things like that, to be able to do more per clock. So they have to pipeline instructions and things like that. And the main thing why this is done is because the CPU cannot CPU is much faster than the memory which is out there. So if you try to do a memory access, it's much slower. So you need to be able to cache, do speculation, do pipelining, do out of order and everything, so that you can kind of mitigate the effect of that memory access, which is pretty slow. And so I just give an example here, right? I mean, if you say take a Xeon V4 E5 socket, which is slightly old, I think it had a maximum memory bandwidth of 76.8 gigabytes per second with the 4 memory channels of DDR4 which it had. And that 3.5 gigahertz CPU pipeline of it had to, I mean, retired around four transactions per instructions per cycle. And if it has to do that, and it has to be fed at around 56 gigabytes per second per core. So that's a lot of memory which you have to give for particular core. And we are not even talking multi-core here. So you can imagine, I mean, if the socket itself can only handle 76.8 gigabytes per second, and if you have to feed each core at 56 gigabytes per second, that becomes a huge challenge, unless you can do all these things like caching and speculation and things like that. And the other need for speculation, I think, is the caching also, right? The caching also is now become a hierarchy, because it's expensive to maintain the SRAM rather than the DRAM. So the L1 to L2 to L3 latencies, I think, are higher. I mean, better than memory, but still I think you get more and more latencies as you go into the outer layers of the cache. And code also causes issues, right? So if you have in the code, if you have branches, then they can stall the pipeline. I mean, the processors today predict for a particular path. So if you're taking a branch in the code, then the processor predicts saying that, okay, you're going to be taking this path most of the time, and kind of optimizes for that path, and then if it goes to the other path, then it has to flush that whole pipeline, and then it has to proceed again on the other path which is there. So these are challenges which microprocessors have faced, and they've kind of handled them pretty efficiently, I think, over the last few decades. But then they've started causing issues in terms of security. I think the microarchitecture, which is what implements most of these things in the processor, is supposed to be like kind of invisible. I mean, you're supposed to not know what is there in the caches. You're supposed, as an application writer, you're not supposed to know what are there in the caches. You're not supposed to know that there's an out of order processing happening, because everything gets retired in order. I mean, the instructions get retired in order, so you don't really know there is out of order processing happening. You don't know there's speculation happening, because speculation is not committed unless it's correct. It's decided that it's the right thing which has happened. I mean, and the branch is the right one taken, and things like that. The transient execution is discarded. I mean, as far as you know, there's no trace of it, and you can't do anything about it. But then Spectre Meltdown have the attacks have kind of turned these theories on the head, right? I think people are now getting very smart in terms of being able to uh, some of these researchers who did find the Spectre and Meltdown attacks. They've actually gone through the whole micro architecture in terms of the documentation from Intel and AMD and others, and figured out areas where they can actually see the cache behavior, right? I think cache, even though the cache is not directly visible to applications, you can, based on the cache behavior, you can figure out whether a particular data is cached there or not. And there are a lot of attacks which have been uh, done using this kind of knowledge, that the fact that the and this is based on timing. Basically, you can do a timing thing of the cache and know that whether what you have is in the cache or whether it goes to memory for that. And so if you, some of these speculation things, you might speculate such that things which should not have happened are still in the cache, and someone doing a Spectre Meltdown attack can actually go and see that, okay, things are in the cache. So they can generate that kind of attack where they can find out what is the data which is kind of secret. So these are very complicated attacks, I think, based on cache timing and things like that. And yeah, if you're interested in this, I think it's a very deep area. I think you can probably go and read both Spectre and Meltdown. There are some very nice papers on that to find out how they um, they are tackling them, I think, and how they are causing these attacks. And they're not too complicated also. I mean, actually, if you read them, you will find that they're not as complicated as it's made out to be. And it's probably, it shows that processors, I think, have the processor designers didn't think of some of these things and how they could be exploited by people. And a lot more of this is happening. I mean, Spectre Meltdown was just the beginning. We had a Spectre V1, V2, V3, V4, I think. I think Meltdown also had a V2 part of it. And then there are more and more of these kind of things which are tackling the microprocessor, microarchitecture, right? I think they are actually, people are looking at each of those things in the microarchitecture in terms of caches and other things which are there, and then attacking them. So it's becoming a huge challenge. I think even Hennessy and Patterson talk about this in their talk. And I think one of the suggestions, I think, from the RISC-V community is that the fact that we are making everything open source will make things better, because things will people will find out some of these issues faster and be able to resolve things quicker, I think, and it won't be so proprietary as an Intel or an AMD kind of implementation. But yeah, I'm not sure if that really solves all the problems. So the fact that we have speculation and all these things in the architecture, I think you will continue to see some of these attacks unless we can get away from this kind of microarchitecture. So these are some of the challenges. So I think I'll stop here in case there are some questions before I move ahead.
Hello, sir.
Yeah.
So, actually, I'm working in this domain of security challenges of the cache memory. So
Okay.
I'm focusing right now on the low frequency attacks, like the
Okay.
key press
The
logging
side
and
channel. Yeah.
yes, sir, yes, sir.
Yeah.
But not the encryption decryption retrieval, the key
Okay.
retrieval, because they are high frequency ones. I'm focusing on the key presses and all basically.
Okay.
So what I'm doing is I'm working on the detection part of it, not the mitigation.
Okay.
So the detection of attacks based on certain event counts of the cache memory, like the
Right.
misses and everything.
Right.
So
Right.
I'm working on reducing the granularity of the monitoring. I mean, the current work done is mostly focusing on monitoring the event counts of the entire system or the program or process as a whole. So
Right.
I'm working on reducing the granularity to certain sensitive part of the code and only monitoring that section or something like that.
Okay.
So what I'm struggling right now is to come up with some lightweight tool to monitor, because to reduce this granularity so much to the only most sensitive thread, which is only doing the highly secured or confidential
Right.
instructions, to only monitor that section, we need very fine granularity. So
Right.
right now I'm using the Intel vTune profiler to monitor these events and everything, and that is a very heavy application. So
Right.
much is very tedious to work on edge devices and everything. So is there any of your inputs on coming up with a low, very lightweight tool so that I can work only on a particular thread and monitor events of that thread at the microarchitecture? Is it possible to come up with something such lightweight which can be implemented on the edge and everything? So any such inputs, sir?
I don't have much knowledge of that. I think maybe Suparna might also be able to say, because she's, I think, worked on some of these performance monitoring and telemetry side of things, right? I think there are improvements in that space. I mean, but there are also some of these security issues are mitigated actually by putting randomness into some of these measurements. I think you don't want to expose accurate data to the users, right? I think so. I'm not very sure if you will get better at this. I think in terms of more tools to be able to do some of these things. I don't know how easy it will be, but again, I'm not an expert at this, so I can't say whether there's something happening in that space to be able to get more granular data.
Okay,
I
sir.
don't know,
Okay,
Suparna,
sir.
if you have anything on this side. I don't know.
No, I'm not able to think about. I mean, you're talking of performance counters is what you're
Yeah.
really using for monitoring. So you really need some advanced. Yeah, I think yeah, we need to check.
Yes, ma'am. Basically, event counts. Like I've done the analysis and I have come up to, through my experimentation, I've come up to four major event counts, which have counts which are exorbitantly high in case of an attack. And I've done it in various benchmark scenarios also to differentiate between a genuine attack and a noisy condition, which may
Right.
mimic like an attack scenario. So there are some few event counts which are exorbitantly high in case of an attack only. So
Okay.
only monitoring those
Okay.
counts, and that too only for that particular sensitive thread, can give us a good
Right.
detection tool.
So
So I'm
one thing I would suggest is that I mean, maybe since you want such fine-grained data, it may be better not to use standard applications. It may be better that you probably read the architecture documents and find out if they have some MSRs, model-specific registers, or something like that, which you can kind of read yourself to be able to get some of this data. It might that
Yeah,
might turn
actually,
out to be better.
I was going to suggest something similar, Mohan, because at the core of it, what you do when you get the performance metrics from the CPU is that you ask the CPU to count these events, and since these events are being counted at the CPU by the CPU itself, CPU doesn't have any notion of threads or anything, so it won't be able to filter out anything. You can only choose which
Right. Yeah.
CPU collects the metrics, and all the metrics are thrown out, and you can read those metrics between start and end point, and then use certain software to, for example, OPROF or perf tool on Linux can actually sort differentiate between which of these occur during the scheduling of the thread. And Maybe there'll be some tools that will be able to do that. So probably, I don't know, you mentioned some tool that you were using, and
Yeah,
I
I
don't
think
know.
VTune she was suggesting. So I think it's on the Intel side. The other thing is you might get better traction with some of the open source processors, right? Like RISC-V or ARM. I think in terms of doing some of these things, unless you're trying to attack x86 from a security viewpoint, in which case, yeah, I think you need it on x86. But if your idea is to just kind of do some research in this thing, I think you might be better doing it on some of the open source processors.
Okay, so yeah, got it. So as of now, I had done it on x86 only, yeah, but I'm looking forward to widen
Yeah,
the domain and read about more
yeah,
ARM
x86, I
and
think they also probably a lot of this are like paid licensed software, right? I think VTune and all, I don't think you can get it unless you pay for it. And that's why I think there's not much knowledge about it, I think, which is very open. I mean, you'll have to actually talk to someone who's doing some of these things to be able to get that level of data.
Yes. So actually, it's a more highly encapsulated tool. So
Yeah,
figuring out how the
yeah,
things internally are taking place is quite tedious. So
yeah.
yeah, that is very heavy application. So yes, sir, I will look forward
Okay,
for other architectures as well. Yeah. Thank
sure.
you, sir.
Yeah, thanks. So yeah, going back to the slide. So I think, yeah. So this I just wanted to bring up the security challenges as an area which is getting very interesting now, and probably where we are seeing a lot of work happening, even from the processor vendors, to be able to solve these challenges. I think both Spectre and Meltdown kind of issues were handled in hardware by the newer processors and in microcode. So going forward, I think you'll not see them. I mean, they're solved in silicon in probably the newer generations, but then there'll be newer challenges which are found on some of these newer processors. So you'll see a lot more of this unless the design philosophies are changed, and some of these things are mitigated, I think, in terms of the what is known as the invisible microarchitecture. So these are some of the challenges, like I talked about, I think, on the compute side. But um, what's the answer? And I think, as I think it goes in the song, I think, by Bob Dylan, the answer is blowing in the wind. I think we have to just look for things which are happening, and you will see that there are options on what can be looked at for the future to solve some of these issues. And so what's really happening? If you see the technology landscape, right, on the compute side, we are changing from what were the general purpose architectures like Intel and AMD, for instance, or even IBM Power, to energy and algorithm optimized SoC processors. So everything is becoming like SoC kind of system on chip kind of processors, where you have CPU, memory, IO integrated. I mean, which happens with the mobile. I think we're already seeing it with the mobile era. But then even on the enterprise side, I think you're seeing a lot of this happening with ARM, and then with RISC-V coming up. So that those are some of the enhancements that are happening to be able to handle some of the challenges which the compute side is facing. On the memory side, what we are seeing is that we have had this, because of this traditional von Neumann kind of computing. I think we have had this access to memory being mitigated by these levels of cache, right? I think we've gone up to even 4 levels of cache in some cases. And I think there's this theory that there are 9 levels of hierarchy if you go to a disk, for instance, right? I think there are 9 levels of hierarchy before you get to something. And that is causing a lot of the latency issues which we are seeing, and that is changing now. I think there's some of that is changing to like what Intel has come out with Optane, right, which is the massive persistent main memory. I think even HPE, I think, when it was known as HP, we came out with one of the original work on persistent memory with what is called as memristors, which is analog persistent memory with uh, uh, basically in the material itself, right? I think on materials which have that memristive capability, we could use to be able to store memory and then store it persistently. So that is happening a lot. I think there are a lot of technologies in the space like PC RAM, MRAM, which is the memristive RAM, and then spin torque RAM and things like that. So there are multiple such material properties which are being exploited to be able to get this persistence of main memory. So that's a significant effort which is happening in the industry, and it's been happening for more than a decade now. I think I am hoping that we are close to a point where we can actually see some of these in practice. I mean, apart from Optane, I think we'll see more of it in practice, and I'll talk why later in my presentation too. And then on the communication side, I think we are changing from electrical signaling, I think, which causes a lot of this mess, right? I think in terms of cabling, and also the energy and which is consumed by some of these cables, I think is huge. So we are changing from this electrical signaling kind of communication to integrated photonics. So if you can have an SoC where you have compute, memory, IO, and all that communicating to each other through integrated photonics, you can reduce the power envelope also significantly, and you can get very good latencies and bandwidth. So that's some of the things which are happening on the hardware side. On the software side, what has happened, and this is probably slightly old, but what we have seen is that we have seen the change from the transactional databases like Oracle to Hadoop and Spark and things like that, which have been done doing more of the unstructured data management. So we've gone from the SQL era to the NoSQL era, right? I think so. There's a lot of the software which has already changed to be able to handle the requirements coming from this social networking era, as I call it, I think, and software has changed for that. But then a lot more needs to change, and a lot more is changing. I mean, as we go forward to be able to handle some of the challenges that we saw in the previous slides. So I'll just talk a bit more about some of the things which are happening, which kind of give us motivation that we can solve the problems which we've been seeing. So the first one is this persistent memory. I think even Suparna can talk very well about this. She's worked on this, I think, quite a bit. And I think memory and storage are converging. I think it's an area which has had a lot of work over the last decade or so, I think, and this shows basically the levels of cache, right, or levels of access before you get to a disk or a tape or something like that. So if you're accessing some registers within the processor, you're just probably taking a nanosecond or so or less. If you're going to an SRAM, you're taking 5 nanoseconds to get that data. If you're going to DRAM, it's 100 and so on. So by the time you get to a tape, it's like multiple seconds before you can actually get to the data on the tape. And the other thing which we see is that on the left hand side, if you see, is it's all volatile within the computer, I think, when you can access memory. But when you go outside the computer and you go to a disk or a tape or something, or a or even flash, it's persistent. So the idea is that if you can bridge this gap, right, SCM is something which is coming in between. I mean, right now, I mean, which is what does SCM stand for? Suparna, I'm just
Storage
losing.
class memory.
Yeah, storage class memory. Yeah. So storage class memory is something coming in between, which is like Optane and all and things which I talked about, right? So it's closer to memory than to storage in some sense in terms of the latencies. So you are able to get better bandwidth and latency out of it. And right now, if you see operating systems, I think operating systems start getting challenges when they have to access memory, which takes probably more than 500 nanoseconds or so. So if the memory is of the order of 500 or less, I think they can handle it, and they don't time out or things like that. Even kernels can handle that kind of memory access. So we are seeing that more and more that the storage class memory, I think, is coming into the realm of memory rather than storage, even though it is persistent and has the properties of storage. So if we can do some of the things which storage does, right, the rich data services which storage provides, like RAID and other things, and if you can do that with memory, I think we can actually unify both memory and storage, and that's kind of the holy grail as far as some of the researchers who are looking at this area. And I think the slide below, the picture below, I think basically shows kind of the same thing, that SCM is coming in between DRAM and disk, and it's increasing, I think, right? So there's more of SCM which is coming in at some point, and at some point we might be able to merge DRAM with SCM and then just have SSD outside or something like that. And maybe at some point we won't even need SSD if we can have everything as storage class memory out there on the fabric. So that's kind of where things are heading. The other thing which is happening is this on-package DRAM. So you would have heard maybe of HBM and things like that, which are coming, where high bandwidth memory, where there's I think lesser memory than DRAM, but you can have it pretty very close to the CPU, and the latency is very low in terms of accessing some of this on-package memory. So it probably provides another level of memory access and makes the system more kind of NUMA. But then I think the expectation is that over a period you will see DRAM maybe going away, only have HBM, and so you may not really increase the number of layers as you see it. It might be just on package memory and SCM, which is outside in the long term. So that's kind of the vision which we are going towards. The other thing on the fabric side, I think on the physical side of the communication, I think what's changing is, like I said, photonics, right? I think you're seeing a lot of the photonics communication happening on the silicon photonics happening now. So you can have on the chip itself, you can have communication with photonics instead of copper wires there. Photonics, I mean, the optics has always been there outside, I think, when you have kind of long running cables, right? We have already always seen that, but now it's getting into the area where you can actually implement it on a chip very efficiently, and the conversion from electrical to light is also becoming pretty good, I think. And so we are seeing a lot more of research happening in this area. The optical switches are also what are known as high radix, so in the sense that you can have a lot of ports on them, and because you can have a lot of ports on them, you can actually create a topology of network, or a network topology, which is kind of low diameter, right? What low diameter means is basically that you can have a lot of nodes which are there, compute and memory, on a single kind of fabric connected through optical switching, and kind of have similar latencies to each of them. So you could have pooled NVM, for instance, right? If you have non-volatile memory, and if you can pool it, you can put it in a fabric and then have compute attached to that non-volatile memory. It can, any compute node can talk to any non-volatile memory at almost uniform latency because of these optical switches. So that's kind of, again, a vision which we are working towards. Locality will still matter. I mean, while this will make sure that you can actually access any memory at kind of similar latencies, the fact that we have things like HBM, which I talked about, and I think here it talks about HMC from Micron, where you have memory which is very close to the processor, you will still have some of that. So you will still have that kind of non-uniform memory access, where if you want something very close, you will stage it in your HBM or HMC and do processing on it. And if you can always get something from a farther memory if required into that memory which is close to you. So that's the kind of application thinking which we have to use to be able to use some of these new things which are happening in hardware. The last point which I want to bring out on this slide is, I think, the table, right? I think the table gives you an idea of why optics and photonics is coming. I think the fact that the energy is becoming a huge challenge. Like I said, I think if you create these huge processors and huge systems, there's a lot of power which is getting spent on them. And if you see, even in the high performance computing, right, we talk of exascale computing and all that, but it's not without limits. I mean, even in exascale computing, we are always talking of an energy per watt kind of, I mean, a power performance per watt kind of restriction, where we are saying that you have to limit within a particular wattage some of these systems. Only then you can call it a real exascale system, because you can't expect these data centers to supply the amount of power to do exascale computing if it is like beyond the realm of that particular data center, right? So, and so that's a very important area where focus is there, to be able to reduce the power, the energy, and rather than just going and trying to increase performance without thinking about it. And the challenge which happens with communication is that communication takes a lot of energy. So if you see a compute within the register, it's like if it takes a picojoule, for instance, a DRAM read write takes around 16,000 picojoules. So it's takes a lot of energy to be able to do that kind of computation. And so if you can move to that photonics kind of fabric, I think it reduces the picojoules which we require to be able to do this kind of communication. So that's another kind of trend from the physical hardware side, which is happening to be able to get to better performance, and so that compute can actually access, uh, as compute gets faster, it can actually access some of the memory and other things on the fabric faster as it needs to. So yeah, this slide I think gives the reason for the motivation for a new fabric, right? So I think what we talked about with photonics is the physical part of it, but then we also have to make sure that the way compute or the CPU talks to memory or IO is what we call as the fabric. And if that has to kind of handle the higher demands which are being placed by this compute which is there. And so if you take the example of a typical server, right? I think now, like I said, we are going up to 64 plus cores, for instance, they are increasing. But then if you see DDR is one of the technologies which is still a parallel kind of bus kind of technology, right? And it requires a lot of pins on a single, so it takes a lot of die area to be able to put those memory channels on a particular chip. And so in typical enterprise processors, you will see around 6 to 8 DDR channels which are there. So which kind of limits the amount of memory which you can have close to the processor also. And it also limits the amount of bandwidth, right? I mean, the cores have a lot more ability to do things, but they are constrained by the amount of memory that they have and the bandwidth of the memory that they have close to them. Similarly, the number of PCIe channels, I think, have been the PCI Express, the IO channels have been increasing, but again, not in the same range as the way that the number of cores is increasing. So the cores has increased at a rate where it's not able to, I mean, it can really overwhelm the amount of IO which is there on the device. So how do you handle demands of things like 100 gigabit? We've moved from, when I was starting, I think we were at, we even talked of 10 Mbps and 100 Mbps networking, right? And we are now moved to 100 gigabit networking, and people are saying that that's not enough. We are moving to 200 gigabit networking and 400 gigabit networking in the future. So I think the demands which are placed on the network is becoming really huge, and the core needs to be able to access some of that fast enough to be able to get to those real bandwidths from an application perspective. So those are the balance is kind of degraded, right? I mean, the compute is not able to really use the memory and the IO well enough to get application performance. And another slide which kind of shows this graph, which shows this is the fact that the DRAM bandwidth per core has been kind of going down. I mean, the number of cores has been increasing, but the bandwidth you get per core is kind of decreasing. So we had almost like 6.5 in 2012, and now we are at the range of almost 3 gigabytes per second per core. So that's pretty low. And then IO also is decreasing at a similar rate. So even though the compute is increasing in terms of number of cores, the cores are not being fed at the bandwidth which we want them to be fed at from a both memory and an IO perspective. So these are all motivations for a new fabric, because both DDR and PCIe is kind of not able to meet what we are seeing as the demands, because they are constrained by that CPU chip which is there, and we are not able to get the bandwidth which we want. Any questions? So what this is doing is, I think this is kind of again motivating the fact that we need new protocols, right? I think DDR and PCIe is not scaling. And one thing which we have seen in communication protocols, I think similar to the old paradigm, right? That old technology keeps coming back. I think we had this thing about serial communication long back, and then we went to parallel bus communication with PCI, and then with DDR. Uh, Both were like kind of parallel buses, and then PCI again changed to PCI Express, which was a serial. So I think we changed back to serial because we could the fact that we had to synchronize among these multiple kind of lanes was causing an issue for communication. So a serial link was deemed to be better, so we went back to serial communication with PCI. So now again, I think for memory also, from the chipset, I think there's this thought that maybe it doesn't make sense to have a parallel kind of protocol like DDR, and can we reduce the number of pins which are there on a particular chip, and then move the memory out of the box itself, right? So that's kind of the thought process which is happening, and that's where some of the newer fabric protocol work is happening with Gen Z. Is a new fabric which HP actually came up with, and then there's an industry consortium around it, and then Intel now has I think started something called CXL, which is kind of taking all the good features of Gen Z, and it will probably become the more standard fabric of the future. It's called the Compute Express Link, and again HPE is part of that consortium too in terms of and it makes more sense, right? I mean, even though HPE came out with the idea of Gen Z, I think it's being not being a processor vendor, it's difficult for HPE to actually influence that communication from CPU to Gen Z as a direct fabric. So we had to implement kind of bridges in between to be able to do the compute to be able to do the communication. But with CXL, I think since processor vendors are getting involved like Intel and AMD, it becomes easier as a fabric which is directly from the compute down to memory and IO. So those are changes which are again happening, which will allow compute to kind of get disaggregated, right? You can have compute on its own and at some level, and then you could have memory and IO at maybe on the fabric, and then if you could kind of democratize the communication, right? So everybody on the fabric can access some of this memory and IO, then it makes things pretty easy to scale applications also, which are there on the compute side. So that's what is happening. The other thing which is happening is accelerators. So I think we have seen this trend, I think, with NVIDIA, I think with GPUs, I think, and accelerators. And as technology is evolving, I think with machine learning and other workloads which are more amenable to this accelerator model, where a general purpose CPU probably does not do as well as an accelerator. I think we are seeing more of these accelerators like FPGA accelerators, GPUs, ASICs, and all that. And so you could now imagine if these also need access to memory, and if that's all on a fabric uh, or IO, which is on a fabric, then I think it makes it kind of easy to build a model where CPUs interact with accelerators and do some kind of co-designed kind of logic to be able to access memory and compute on it. So that's where uh, the architecture is kind of heading. So this is just one more slide on CXL. I think the use cases. So I won't talk more about it. It takes a lot of I think time to be able to go through all the CXL techniques. But CXL, I'll just give one or two high level points around CXL. CXL is going to be very similar to PCIe. It's going to leverage a lot of the PCIe protocol, in fact. And so if you have a slot which is supporting PCIe, that same slot can now use CXL also. So that makes it a huge advantage, I think, from a CPU designer as well as from an application this thing perspective. And that CXL device can now support multiple protocols. So CXL.io corresponds to a standard PCIe. It can also support CXL.cache, in which case, if an accelerator has a cache, it can kind of provide access to it to the. I mean, it can actually access the memory of the processor and then cache it within itself. So that's kind of what a CXL.cache does. And then there's
Hello.
CXL.memory. Yeah. Yeah.
आधार ना म्हजे कडेन आसा तुगेलें आधार हांगाच आसा काय दिसता म्हाका हय हांव घेवन येता ते फोटो बिटो घेवन येता ओके पण
Look,
हांव
is
तुका सवाय
someone
तुमार
not on
फोन
mute?
करता ओके ओके आय जस्ट कन्फर्म विथ हर that even if internet is not there we can do the job.
Hello, someone not on mute?
Yeah, it's okay now. Go ahead.
Yeah, I don't know. So are there any questions so far? I mean, so I think basically CXL is introducing multiple things like IO and cache and memories to be able to provide a cache within an accelerator, and also for a processor to directly contact memory, right? So if a memory is outside the processor system, I think it can access that memory through CXL.mem kind of protocol. So that's another thing which is coming. In the first, I think CXL is still very nascent. It's not yet a standard. There's a CXL 1.0 which is out, and a 1.1 I think also is out now. And you will see initial process with CXL 1.1 specification. But CXL 2.0 is when you will see this memory class of devices and processors being able to talk to memory on the outside through a PCIe device kind of thing. PCIe type of device kind of thing. So that's kind of coming in a future this thing. But that's where hardware is going. So it gives you an idea of what software needs to do to be able to use some of these things. I think I'll probably stop here. I think I can come back and finish the remainder of the presentation. Otherwise, because there's still quite a bit of slides I think left. So we can probably stop at this point. If there are any questions, we can take now. And so, are there any questions?
Yeah, hi.
Yeah.
I have one question, but I don't know if there's an answer to this.
Sure. Yeah.
So, yeah, the CXL is really exciting. I really like. I mean, yeah, interconnects have been. They really need an upgrade, but I have this feeling that the CXL might turn out to be another Itanium. I don't know. It's the same folks behind it.
Not really. I mean, Itanium was more of an Intel and HP thing, right? I think HP came out with Itanium, and it was more of an evolution of PA-RISC to that Itanium generation. And I think Intel came on board, and it was more of a two-party collaboration, right? It was not an industry thing as such. And then later, I think we had a few more like Bull and others who also jumped on the Itanium bandwagon. And actually, to be frank, actually Itanium has been very successful. I think people don't realize it. You see a lot of academia kind of dissing it, but if you go and see actually the amount of servers which we have using Itanium, and we still sell them today, and it's a huge profit making business, like the way the mainframes were for IBM, right? So it's not just because it didn't serve some open source purpose or something like that. I think it's not to be completely dissed. It was a different technology. It's probably something which might come back for all you know, as we go ahead. But then yeah, and I don't think you can really relate CXL to Itanium. I mean, CXL is more of an industry thing. I think both Intel, AMD are on board. I think and I think even RISC-V and others are also part of the CXL consortium. So I'm more hopeful that it would be an industry standard. It is an industry standard even today, and there is talk of even putting persistent memory on the CXL bus in the future. And so yeah, there is hope. I mean, of course, I cannot guarantee that things will not change. Uh, you can never say which technology is successful and which is not, but it it has all the right things going for it right now.
Yeah, either way, the problem has to be solved, right?
Yeah, yeah, the problem has to be
Definitely.
solved. So I think Gen Z was a response to that, but it was difficult to get the industry behind it. CXL has a better chance of success because it has all types of folks behind it, right? It has the processor vendors, it has the hardware makers, ODM makers, and then it has even the cloud vendors, right? Like Google and all also behind it. So it has enough push for it to become successful. Yeah, we'll see.
Sure. I mean, I don't mean to diss Itanium or something, obviously.
Yeah.
I think it was ahead of its time. That's what I like to call Itanium. But
Yeah.
yeah, I really hope CXL succeeds because
Yeah.
DRAM, that interface is not scaling for sure.
Yeah, exactly. That's the problem, right? I mean, the number of pins which we have is huge, and it's not really scaling. So you're not able. We are even to get the both from the physical part of it, right? In terms of the fabrication of DRAM, I think that's not improving, and then we are not able to get the bandwidths also because of the number of pins. And with DDR5, I think I don't know after DDR5 what. I mean, nobody really knows. So uh, I think it needs a change there.
Yeah, definitely. So is there any inbuilt support? I mean, now that you have so much support for caches, directly accessing caches over the interface, do they also include some sort of cache coherence protocols as part of CXL?
Yeah, so that was something which I think HP at least has always been interested in. So when we talked about Gen Z, I think we were talking of introducing cache coherence in that to be able to connect any devices on that fabric, right? CPUs, accelerators, memory, and things like that. CXL has been a bit more restricted in terms of what they can do. Intel has kind of tried to keep their UPI fabric, which is actually connecting the CPUs separate from this IO fabric, which is CXL. But slowly they are coming around to the fact that yeah, they might need to introduce some level of cache coherency to be able to handle these things. And so there is things being built into the spec now with 2.0 and 3.0 where you might see some level of cache coherency coming in.
Yeah, yeah. This is a tricky business. There's one more question that immediately comes to mind. So,
Yeah.
is CXL a synchronous protocol, or is this going to make the system something sort of? Is the interconnect going to look more like a network on chip, or something like a network on system? Like, is this packet based, or is this
It is
wire
packet
based?
based. So it is PCIe kind of protocol based. So it is a packet based protocol. Even Gen Z was designed to be a packet based protocol. So
Okay.
yeah, it's not kind of connected kind of thing. I think, right? I think you might implement it connected through some kind of packet mechanism only. I mean, like the way TCP and all does, right? At a higher level, there'll be some higher level abstraction for connected this thing, but at the lowest level, it is not really connected. It's a packet flow.
Yeah. Great. That's quite interesting. Thank you.